And then after we've done our compress, we would then do this. So while bucket sub I is occupied, then we'll say I equals probe I. So we'll apply whatever probing function we want. At the end of that, we find an empty position, right? So then we say that bucket sub I is equal to X. Find works pretty much the same way. Find X, H equals hash X, I equals compress X. And then we'll say while bucket sub I does not equal X, then we're going to do I equals probe I. Now we do have to have some kind of way to stop here too. So we might stop if we made a kind of continuous lap around the entire hash table. If we've probed all possible things, I'll just add in here, if we've probed everywhere, stop. We'll return null. So usually when we're probing, we'll go all the way through once. But after we've lapped the original position, then we probably aren't going to find anything more. Quadratic probing leaves greater spaces in between things, but it won't necessarily land back on the space that we're at. But we'd basically would have to say after we've probed everywhere, then we quit probing, and then we would of course return the bucket sub I. Okay. So that's add and then find. And of course in all these, as we're adding things, we'd always check our loading factor and see whether or not we've actually exceeded our loading factor. If we had, then we would rehash. Okay. So let's talk about these functions themselves, what the hash code might look like, and then we'll talk about what the compression functions look like. We might actually have enough time to implement one if we go a little bit over. I know you want to see one implemented, or you want to just leave it at pseudocode? Actually, I could do both. Your book actually has a pretty robust implementation that uses templates. The book actually has a template version of this. We'll talk about these functions, and then I think that'll eat up all of our time that I wanted to allocate to class, and I want you to have some time with your partners, especially since this next pair programming part of it is kind of challenging. Because I asked you to look up how to do it. I'll give you a basic idea of how it works. But
look it up. But since it's tougher, we've got a larger amount of time, right?
Yeah.
Till Tuesday.
Till Tuesday. No. I did make it do on a Tuesday, but not next Tuesday. All right. So here is But let's talk about hash codes. So hash of X. Your book gives you a whole host of them, but there's basically two basic strategies. You add up things. So it depends on what you're hashing. You would write a hash function that would work well for the data that you are hashing, and the way that you will know that it works well is that it has few collisions. So you have to try it, observe it, make a probabilistic argument about the collisions that you're seeing, and so on. But there are some that are kind of tried and true. So say, like, suppose X was an integer. Well, now, if you're going to hash an integer, then that seems like a silly thing to do. But one thing you might do to hash an integer is you could count the number of binary ones in the integer. You could count binary ones. You could add all the digits together. Or you could use it to seed some kind of a random number generator and extract the random number. So you could use it as a random seed form. And your book gives you some more of them. But there's any number of things that you could do with them. Now, generally speaking, if we had integers, we probably wouldn't be doing this because it's cheap to compare them. At least the hash wouldn't be as important. So something that would give you low numbers of collisions would be a good idea. There are other techniques that you could do. You could, say, you have this number of digits in the number, and then you could raise prime numbers, like the first few prime numbers, to those powers and add them together to get a big number. Just some kind of transformation on the numbers. And it's really going to depend on what the distribution of your integers look like. But these are just some ideas for how you can carry out that kind of hashing. And in fact, you are going to get a pair programming exercise to do with hashing. It's not going to be this week. It'll be after this next one is done. So I think that's our last one, actually. 8 will be our last one. So you'll be one more pair programming thing where you're going to be given a C implementation of hash tables. And then you're going to be asked to explore various hashes and make observations about which ones are best for different kinds of data. So I've got you a generic one that I wrote in C, which is part of why I didn't plan on implementing one tonight. It's because I got a nicer one where I could sit down and think and make comments and stuff. But it's generic, so I wanted you to see that you can do generic programming in C. So, your temptation would be to use some kind of template. But through the judicious use of void pointers and function pointers, you can do polymorphism in C, which is what I did.
Yeah.
You're like, goody, right?
I like
Okay, so what about a string? Well, it turns out that most people try to add together the characters in a string, and that's a terrible hash. It's something that has high collisions. So what the book recommends, what I also recommend, is sort of a polynomial hash. So if you had a string x, and you had like x sub I is the ith character, then you could do something like this. You could say, take a times x sub 0, and then, x sub 0 plus some constant a, and then multiply that times x sub 1, that's wrong, hold on. How's it go? I'm going to cheat. So I know the book had this one in there. And it's one of the things I do like about this book is it gives you this polynomial. was going to fail spelling bookshelf, didn't it? It's odd that it didn't take me back to where it was. There it is, polynomial hash codes. I think you'll see why I don't ever get this correct. I'm going to try to remember it. I always have to look it up. So it's x1 plus a times x sub 0. That's what I was missing. See, I always mess it up. So the pattern goes like this. So it's x1 plus a times x sub 0. And then the next term out is x2 plus a times that one. And then we take the next one, which would be x3 plus a times that one. And we just keep building it up like that. And you get a really huge number at the end of it. Here we're treating characters as integers, obviously. And then they point out that if you're talking about English letters, there are some magic numbers that you can use. So a is a constant. You see that you have some experimental values for them. Yeah, we have done experimental studies that suggest 33, 37, 39, and 41 are good choices for A when working with character strings that are English words. So if you're hashing English, then those are good values. We know they're good values because they've tried a bunch of them and those seem to work well. When you get into heuristics, you get unsatisfying results like that. So for English words, and it's different for different languages. So 33, 37, 39, and 41 work well for A. This is the basic idea behind compression functions, hashing functions, what they look like. If we were to look at compression functions, let's go ahead and show you the book's listing for those. So I want to point out something about their version of this. This is not actually what I have seen called the MAD method of compression. So the obvious way to do compression, of course, would be to do the mod, right? I want to get a number between 0 and capital N minus 1. Modulus is the way to do that. If I take the number, whatever I got from the hash code, and I mod it by n, that will give me an index, regardless of what it was. Now, if they say down here, if a hash function is chosen well, it should ensure that the probability of two different keys getting hashed to the same bucket is 1 over n. Choosing n to be a prime number is not always enough, however, because if these are a repeated pattern of key values of the form I times n plus j for several different i's, then there are still collisions. In other words, this thing is susceptible to collisions. So there is this one, and more it tells you that the better way, it's called the multiply, add, and divide, or MAD method, which is A times K plus B mod n, where n is a prime number. And A and B are non-negative integers randomly chosen at the time the compression function is determined, so that A mod n does not equal 0. Well, the way I've seen this usually written out, and this is the way that I've implemented MAD, is for the MAD compression function, what I've had is I've had I do this, I do A, K plus B, but then I mod by some prime number P, and I take this entire thing, and then I mod it by the number of buckets. That's the way it's usually implemented. So if you look around, this is what you'll usually find, is the absolute value of A, K plus B. And the other part of it is that A and B are both less than P minus 1. So that way, we know that this is not a multiple of these, and that reduces collisions. So then you'll see that this side of things, which I wrote over here on this board to kind of illustrate that, isn't really all that great in terms of what we can prove. We can prove this so long as we keep things spaced out and that we don't have a lot of collisions, then a hash table will basically be a constant time device, which is great because we can do a lot of things very rapidly that way. But we go over to that thing and we discover that we can't really provably make that happen. We can only make it kind of probabilistically make that happen. If you were going to make an argument that your hash function was good for a specific kind of data, then you would have to build an argument that the distribution of possible data points that you were going to encounter were such that the probability of generating the same I value was low. And it'd be a combination of your hash code and your compression function. So see, there's a bit that goes into it. The good news is, though, that simple seems to win in these. When hashing strings, this coupled with that will work phenomenally well, with very few comparisons being needed. And that's what you're trying to avoid, is string comparisons. Now, of course, when it comes to generic data types and generic structures, sometimes the red-black tree is the way to implement these things if you know that you need to do more searching than hashing. But hashing is an optimization thing. It's an optimization technique. It's very handy, too. All right, any questions on hashing? It'll be coming back. You'll have a program to do with it. Really, the program is I'm going to give you an implementation of hash, and then you'll be implementing multiple hash code functions and multiple compression functions, and then trying different things and seeing what you get. So you'll get to see one in action. And like I said, the book does have a C++ hash table implementation in it. So if you want to see how it's implemented, you can go and look through this, but it's really not all that exciting. It's pretty much exactly what I've described in the pseudocode up here. Well, if there are no questions, I'll go ahead and talk about the next leg of the pair programming example and then let you work with your partners. So you have the first part that's due tonight, and this part that will be due later than tonight. That's also due tonight. No. Your new assignment's due in 20 minutes. Go. Woo! Have you seen the memes with how to generate perfect code and Kim Jong-un sitting there next to the guy at the keyboard?
What is? Show it to us.
Or how to? See if I can find it. How? See if I can find it. Let's see.
Meme.
Yeah, there we go.
I'm stressing by me.
No, my favorite version of that meme is the caption said, either it will execute perfectly or you will be executed perfectly. Or no, either it executes flawlessly or you will be executed flawlessly.
It's funny but sad.
Yes.
Sad because it's true.
Yeah, also in world events with code, Pope Francis just became I think it was last week or the week before, became the first pope to write a line of code.
What? Cool.
In Bible code, no, rights, line of code, less crazy. Line of death, line of code. Gosh.
I've read code.
There's variety there.
Papa Francis.
I'm sorry.
It's the other thing. You have to remember that Italian for the Italian informal title of pontiff would be Papa, not Popo. Popa in Italian means potato.
Potato Francis.
Wait a minute, let me see this.
So let's see. Where's it, David? There's a programming for peace event. Let's see if they have the line. One of these have the line of code. It's basically like a hello world kind of thing. It says something like code for peace in Latin.
Wait a minute, there is no word for potato in Latin because they didn't have potatoes.
No, but it's in Italian.
Huh?
In
Oh,
Italian.
Italian.
Yeah.
Then-
There certainly is a word for potato for it in Italian. It's not even his actual official title, though, right? His official title would be the bishop.
Patata. That's what I got there.
Let's see. I was disappointed because they chose JavaScript for this.
Oh.
And see, if he had written it in C, that would have been a holy C, right? It would have been-
Oh, yeah.
There we go. There it is, right there. There's his line of code.
Set screen pour la pop.
Yeah. So that would on a JavaScript screen would print that string.
Is Java the one that has like a really crazy print statement to like print something?
Well, lots of them do that.
I don't know. I saw something that was like this language to like just print something. It was like very long.
Well, in Java, it's system.out.print.
Yeah, that's something.
Yeah, and then it's like in C#, it's console.write or console.writeLine. Or in Java, print line if you want to print and have a new line. But, yeah. Anyway, that's not what I wanted to go over, just sort of random. 472 bits of entropy in that password, which means it would take the Summit supercomputer about 400 years to get it.
So no one's gonna steal the information from your books.
That's right. And it's easy for me to remember. That's the other part. Past phrases, not past words. It's a complete sentence, so it's really not that hard to remember.
Probably, I mean, sentences are easier to remember than words, right?
It's certainly easier to remember than words that you substituted some of the letters for numbers.
Yeah.
Alternate uppercase and lowercase.
You must use one character.
So this will be due on April 16th.
Sweet.
So you've got 12 days from now to do it. And then number 8 will follow fresh on its heels. So this is to implement 20 questions. So the way that your program should operate is it will start off and it will ask a question, a yes or no question. The user will answer yes or no. And then, and I mentioned that as being vague in the description and in the how, but I gave you some places to look to get you started. Weirdly, the Wikipedia article on 20 questions is like really super detailed, but it's actually not a bad place to go. Anyhow, it should ask yes or no questions. So what this will be like is a binary tree. The interior nodes of the tree will be questions, and the leaf nodes will be answers. So then, if the user answers yes, you'll traverse left. If the user answers no, you'll traverse right. And then, if you reach a leaf, then that's your guess. But if you don't reach a leaf, then you ask whatever question is there. And you keep doing that until you reach a leaf node. If the computer gets it correct, then, because it asks, is it this? That's the last question. Like, are you thinking of, I think I gave you the example of turtle. And then if you said no, then it would ask you, what are you thinking about? And then you'll type in bird, in this case. And then it'll say, give me a question that would differentiate between a turtle and a bird. and then you'd say, does it have feathers? And then it would say, does it have feathers? If the answer is yes, it's a bird. If the answer is no, it's a turtle. That's how the tree builds. So the user trains it each time. Now the other part of it is it needs to store the results in a file. So it needs to store its vocabulary in a file. So that code that you wrote in the first part is going to be used in this one, which is going to have your binary tree storage and loading. Right? It's also going to be used in the lab too. The last graded lab does that.
And it's limited to 20 layers, correct?
No, I said that you didn't have to worry about that limitation. Just let the computer go. So it simplifies the coding.
Oh, okay.
So you don't have to do that.
To 20 minutes.
20 questions. So you can keep track of the number of questions you asked after you got to 20 levels. If you think about it, 20 levels of binary search tree gives you the option to have 2 to the 20th possible things. That's a lot of things. You know, that's, yeah, that would be a bunch. What would it be? That would be, well, over 1 million. It would be a lot, yeah.
Wow. So 1,048,576.
Yes.
1 million and some change.
So, so that's how many things you can do with that. Now, the commercial one does yes, no, maybe. And some of these things tell you how to handle the maybe or unknowns. But you don't have to deal with that unless you want to. You can if you want to. But the basic idea is, like when you start out, when it starts, of course, it has nothing. It doesn't know anything. So maybe you could give it, you could hard code like a default. Like, is it a hot dog? Okay, so we could say that, so you could have something for an initial tree. So we could say like, hot dog. And let's say, in fact, that you were thinking about batteries. So there ought to be a question that would differentiate from batteries.
Can you eat it?
Is it alive?
Can it
It's a
hold a
different-
charge?
Can it hold a charge?
Just to ask a question that
Can it hold a charge? Yeah. You'd want to ask a question, can it hold a charge?
Oh, but that-
And then if the answer was yes, then you would say battery. If the answer was no, then you would say hot dog.
Oh, okay.
And
that's
then-
the real difference.
Yeah, and then let's say that it once again asks hot dog and you were thinking of lettuce. Then you might have, like, you'd replace this node with, is it a vegetable? And then if the answer was yes, then you would say lettuce.
If it was no, it'd be hot dog.
Yeah, and if it was no, it would be hot dog.
Okay.
So you keep replacing your leaf with a question where the no side is the leaf that it guessed incorrectly, and then the yes side is the is what you just learned.
So does that mean like the first question will always be, can it hold a charge?
Yes. It does
Careful
exactly
what you
that.
said.
It'll always start at the top. You could hard code, is it animal, vegetable, or mineral? So you could say like, is it animal?
Yeah.
And then yes, and then is it and then for the no, is it vegetable or is it mineral? And then put a mineral, an animal, and a vegetable in there.
That just seems like a weird leading question.
But that is the standard leading question for 20 questions.
No, I mean, can it hold a charge?
Yeah.
It seems weird.
I think the standard game of 20 questions allows you to ask animal, vegetable, or mineral for the first one, and then from there you ask yes or no
That's
only
what I
questions.
remember.
Could you like have like, you ask them like animal, vegetable, or whatever, and then whichever one they select, you like load a file that's like vegetable dot.
You
tree
could
or
do that.
something? Yeah.
That would be an acceptable thing to do as well. You could have 3 trees, an animal tree, a vegetable tree, and a mineral tree. So that's another possibility. So you can explore the different possibilities. And then, but the ultimate thing is I'm looking that you can use a binary tree to do this. And this would be a binary tree of strings. Remember I hinted that you want to do strings. And resist the temptation to make a question class and this kind of class. An answer class is really just a leaf. So if something is a leaf, it's an answer. If it's not a leaf, it's a question. It's all just strings. Make a binary tree of strings is what you want to do. And then you'll get it. Slowly but surely. Now, what I've done to you is I've given you places to look, including one from Stack Exchange, which is it's the Stack Exchange game development. Someone asked, how do those 20 question things work? And then someone answered. But they gave an answer that is based on doing a weighted binary tree that can actually increase or decrease weights according to the maybe category. So you can make a probabilistic choice. That's harder. You don't have to do that. You're doing a straight up taxonomy tree. Yeah. Another alternate version of this project is one that identifies mushrooms, but I decided against that one. Because the mushroom database actually can build a decision tree that does a reasonably good job at identifying mushrooms, but not a very good job at identifying mushrooms. And I used to give that one because people thought it was cool. And then one person found a mushroom that they thought was an edible mushroom, which was in fact a toxic mushroom. And I did stop them from eating it because they brought it to class. I found this and identified it with the program. It says it's this. I said, no, I promise you it's not that. Because I knew what kind of mushroom they were holding. So if you eat that, it'll make you very sick. Like, well, that's a good thing I didn't eat that. It could have killed me. It wouldn't have killed you, but you would have been praying for death. Most of the toxic mushrooms in Tennessee fall under that heading. You eat one, you might feel like you're going to die, but once your system has been flushed out, you'll be fine. And then some of them, actually no, there's some of them that have neurotoxins in them. But few people eat those. You bite into them, your lips go numb, and your instincts will just tell you to spit that out.
Makes sense.
Anyhow, there's your 20 questions. Any questions?
Yeah,
20 of them.
Yeah, 20 of them. I'll count. All right, get with your partners, start coding, finish up the one from earlier, and then do this one. Maybe everyone will turn it in early. No.
Brandon, we on the same page?
I mean, sort of, yeah, I guess.
Cool.
Do you want me to submit that thing I have?
You want to see?
Go ahead, do it, we'll tweak later. Bigger fish, etc.
Yeah.
Bigger fish.
I'm of the same mindset.
Yeah. Lab 3 is a bigger fish.
Yeah, our lab 4 will actually be somewhat easy for you because you've already got a binary tree storage mechanism if it works.
Yeah.
That's a
We'll already
conditional
have
statement.
Yeah, if.
Well, then you will eventually get this one to work as part of lab 4.
Yeah.
Did you get the file uploaded that I sent you?
Nope. I have the file though. It's on my computer. Wait a minute.
Oh, cool.
It's at home. Let me see.
I already uploaded
I have it on my email though, actually.
Okay, cool. I already uploaded it on mine, but both of us have to upload it. So I just don't want you to like.
Did you change your file?
I didn't change it at all, no. There was actually nothing I saw.
Can you show me how to upload it?
Yeah.
Gmail.
And I didn't put your last name in the header because I wasn't sure how to spell it. Because I know.
Where's it? Right.
Yeah.
That one. And then, you saved it as a text file.
Yeah.
Yes.
Where's it gonna save it?
Okay.
Where is it located? How do I find this out? I haven't used Windows for such a long time. How about I save as? So it's gonna save. Kind of max. Alright. So here's PC. Oh my gosh.
I can show you an easy way to upload it.
Did you copy
Go ahead.
it by any chance?
Some of it.
Hey, you wanna link to your YouTube channel?
You got
So what?
binary
You wanna see my
characters.
YouTube channel?
I would love a link to
Notice
you.
there's an 8 pack.
Could you email it to me?
Characters before and after.
Pellissippi email?
Yes.
Okay. Yeah, I'm with you.
That's boss. Thank you much. Oh, that knocked that terminal over.
See you, Will. See you, Brendan.
Username? I don't know.
Ben.
You don't know your username?
Hey, Ben.
If
If I text you, could you respond next time?
I promise I will.
Okay.
I'm sorry. I'm a flake. I don't text people back. I forget. I'm sorry.
Wait, username like for Pellissippi?
No, it's like C1020B,
Yeah.
and then whatever your
Well, that's
number
okay,
was.
that just means that you have like code characters in there maybe. There's a way to do it.
Dr. Lowe can tell
without-
you.
to remove
Dr.
all
Lowe can
binary
tell you.
characters from a text file.
What is the number for this shell execution?
Oh, for the